My people. So what we're doing here is actually the first question that usually pops up in the Pure Maths Unit 2 paper. This is complex numbers. I feel like I could handle this one, but I would leave this question to be handled by our Pure Maths Unit 2 teacher. This is Mr. Darian Giuseppe. So he will take it from here and he will explain the question for you. So Darian, without any further ado, the floor is yours. What question are we doing here now?
So we're looking at a past paper question, and the past paper question comes from 2016, and I think everybody's seeing the question here. We're getting straight into it. Module 1, question 1, right? So we have here part A. It says that the quadratic equation is given by ax squared plus bx plus c is equal to 0, where a, b, c are elements of the set of real numbers, right? Or rather, the complex roots of the equation are alpha is equal to 1 minus 3i and beta, right? They just give us beta. They didn't tell us what beta was. And then they say in part I, calculate alpha plus beta and then alpha by beta, right? So key things to note about the question. Before I do any question, I always suggest to my students you underline the key things, right, that you're seeing. So you have the key thing, they give you the quadratic equation and they say a comma b comma c are elements of the set of real numbers. That's really key. Complex roots are alpha is equal to 1 minus 3i and beta, right? They say calculate alpha plus beta and alpha by beta. To calculate that, well, we have alpha, but we don't have beta, and that's the problem, right? So we need to try to find out what is beta. How we would go about finding what is beta. We need to know a specific rule. This is a thing that is either you know it or you don't know it. Question?
Right. So because we have the quadratic formula minus b plus or minus the square root of b squared minus 4ac over 2a. With that arrangement, the imaginary part would come from the root of a negative number. So that means all roots must occur with a plus and a minus. They must occur in a conjugate pair.
Yeah, so that is basically the rule that that should come immediately to your mind when you see that alpha is equal to 1 minus 3i, right? That is a root of this quadratic equation. The rule will pop into your mind, but you need this part here. You see, this part here is really key. The rule states that, and I'm just gonna put it down here, right? This is basically the rule here, right? And this is really key. What I have here is, since ax squared plus bx plus c has a complex root, and the complex root is your alpha minus, well, 1 is equal to 1 minus 3i, right? Since it has that complex root, and also because a comma b comma c, those three, right, those coefficients, if you want to call them that, are elements of the set of real numbers, then the roots occur in conjugate pairs. That's really key, right? So what we need to focus on with the rule is that it's a quadratic or it's a polynomial. It doesn't necessarily have to be a quadratic. It could be a polynomial, right? So it could be x cubed, x fourth. Once the polynomial has a root or a complex root and the coefficients of this polynomial are real, your a, b, and also your c. Once those are real, right, it has a complex root, and well, the roots occur in conjugate pairs if and only if the coefficients here are real. That is very key, right? It would only take place if those coefficients are real, right? So that's what you need to know. It's either you know it or you don't know it. So that's why I advise that you learn that rule, you know that rule inside out, right? And well, once you know that it occurs in conjugate pairs, then you move forward. It's really easy to find out what b is. It's just a matter of changing the sign here, right, in alpha. That's what we mean when we say is a conjugate. You need to find the conjugate of alpha, and that would be what beta is, right? So that is what it was. Yeah, because alpha was given as 1 minus 3i, right? So then beta would be 1 plus 3i. So then let's move forward to finding what the question actually asked, right? Question asks us to find alpha plus beta. So let's do that, right? So alpha plus beta would be that. Let me just fix this I. It looks kind of weird, right? And let me just fix it to be in coordination with what alpha is and what beta is, right? So that's basically it. We would just add a real part to a real part. You get 2, and then the imaginary parts will cancel off each other, right? These will cancel, and that's basically it. Simple stuff. This was, I think, 3 marks. So these are easy 3 marks. And then what we do is alpha by beta. That is the next thing to do, right? And you should know this is something something that you could recall a complex number by its conjugate is the real part squared plus the imaginary part squared. So I'm just going to change the signs again here just to make sure that they're correct and they're in line with what alpha is and beta is. And when you multiply these out, you just take the real part, which is 1, right, and square it, and the imaginary part, which is 3, and square it. That will give you 9. So 1 plus 9 is 10, and that's your final answer there. And you could just say, therefore, alpha plus beta is 2, and then alpha by beta would be 10. All right, cool. So let's get into the next question that is here. That was part A, part I, and now we're looking at II, right? So we have hence show that an equation with roots 1 on alpha minus 2, and so this is 1 on alpha minus 2 and 1 on beta minus 2 is given by this equation here. So yeah, let's get straight into it. What we should know offhand here for this particular question is this. There's the golden rule here with this particular question here. You have x squared, right, minus the sum of the roots, right, by x plus the product of the roots. That would give you an equation here. And we can just throw in a little equal to 0 here. But this is really the big gist here. That is what you need to know first and foremost. Then all we're doing is basically, they told us that the roots are this and this, right? So it's just a matter of taking the roots and finding the sum of this and then finding the product of it. So that's what we're gonna do next, right? So we're moving forward again, right? We're looking at the sum of the roots first, and this is how I like to break it down here really quickly, right? We'll get into it here, right? So we have the sum of the roots first. That is this part here. Once we get the sum of the roots, we looking good, and then we look at the product of the roots, right? So the sum of the roots here, we just basically finding the LCM on a B6. There is B6 here we're doing, right? Finding the LCM, and we would have found what is alpha plus beta. You would notice alpha plus beta coming to the forefront when you find the LCM, and also to alpha by beta coming into the forefront. And remember, we found alpha plus beta in part I, right? So we would have found that. So it's just a matter of wherever you see alpha plus beta and alpha by beta coming to the forefront, you're just plugging in stuff, and it really, the question is really straightforward. So we have here, right? So this is what we get here. Finally, when you just simplify everything, your alpha and your beta, right? So you have an alpha plus beta, your substitute was alpha plus beta. We know we got 2 for that, so you substitute 2 here, right? Alpha by beta, you substitute 10 here. And then I also do have an alpha plus beta here, so I substitute the 2 here, right? And then this works out to be negative 1 on 5. So that's your sum of your roots, right? Question almost done. We just now have to find the product of the roots. So let's look at that, right? The product of the roots will be this multiplied by this. And the next thing is the product of the roots. So we're looking at that here. As I said, you're taking the 2 roots and finding the product, right? I didn't bother to find or to really work out the denominator from scratch because you have the same denominator here multiplying here. So I just basically took the denominator that I worked out here. I think in this thing, you don't really have much time in this exam, so wherever you could, make it easy for yourself, you already found it here. If you notice that, you could just put it here, and that answer was 10. If you could recall, you see 4 minus 4 plus 4 plus the 10, right? That leaves you back with 10. So you have 1 on 10 there. That is your product of roots. We almost done here. Now it's just a matter of plugging the negative 1/5 into here and the 1 on 10 into here. So that is what we need to do next, right? Almost done, guys. So this is basically what we would have at the end, right? So let me just fix this here. You have x squared, right? We plug in the negative. Let me just fix that here. Bam, there's a negative, right? We plug in the negative 1 on 5, where we have the sum of the roots multiplied by x plus 1 on 10, right? That is your constant there, equal to 0. But that doesn't really look like what they have here. They're looking a little bit different. So what do we do here? Right, we have fractions here. So what I would do, it's simple and it's easy to see. We just multiply by 10. That's what we did here. Multiply by the 10, and that's how we get 10x squared, right? You have 2x, and it's positive, right? Because in negative here. There's our next thing here, right? This is very key. Don't here, you don't want to put positive here. This is a negative, so you have to remember that formula, right? You don't want to put positive there because that can mess you up and you're going to be worried why I'm not getting the correct answer. And why? It's because you changed this to positive when it should be negative, right? So now, yeah, that's basically it. You multiplied by the 10 and there's your answer here in the end. That's it, right? So you get exactly what they tell you to show. And that's part 2. Really simple stuff. Yeah, so now let's look at the last bit, part B, right?
Argand diagram is a while since I did this one.
Yeah, so this one actually real simple. This real food. This is what it's called. Whenever you see a question like this, they just 1 mark, 2 marks. This is what it's called cooked food. Like they just give you food on a plate. Yeah, that's basically it. Right? So we have 2 complex numbers are given. Right? You have u is equal to 4 plus 2i, and then v is equal to 1 plus 2 by the square root of I. Right? So this is what we're given, these 2 things here. Right? And then they ask us to complete the Argand diagram below to illustrate u. Right? Complete the Argand diagram below to illustrate u. U is what we have to illustrate. Right? So if you look at u is 4 plus 2i. Right? And all you're simply doing is,
so
if you could recall,
when you're doing the Argand diagram, the I is on the y-axis.
Yeah, the I is on the y-axis. Normally, if they would, sometimes it doesn't always give you like the graph, right? Sometimes you may have to just do a sketch now. But I would recommend, when you're doing a sketch, you just indicate this is your imaginary Z, right? And this is your real Z. They didn't do it, but
I will do that too.
Yeah, just for completeness sake. And this is come like your real Z is your x-axis in essence, right? So that is your 4, right? So that's why this would line up with this. And then your imaginary is your 2, right? So this should line up with this here, right? And you label it U. This complex number is represented as a vector. I see that a few times. So that's why I just put this as a triangle, right, in text. So basically,
you put the arrow for that.
Yeah. So this is basically what I do. And as I said, you should, I would, if you don't get a diagram like this and they just tell you to sketch it and you have to actually draw it up, indicate what is your imaginary axis and what is your real axis, and that's it. This is an easy 1 mark, right? Let me see what's gonna happen here. I don't know what's gonna happen here. Right? So we have this, and this is what we have happening here. There is the whole concept here. This is basically the part in complex numbers when we're looking at the locus of the complex number. Anytime you have this here, you see z minus u, right? You just replace u with what it is, and this is the form for a circle, right? That is the form for a circle. The center is represented by these 2, right? The real and the imaginary part, right? And the radius is 3. So just remember, it's a sketch, right? But try to make it. I don't know how you're gonna do a circle in the exam. I don't know if it does have what is this projector?
You work with a compass.
Yeah, a compass. Yeah, so
or the geometry center have a little thing.
Yeah. So you could just make sure, right? Your distances looking a little correct. This should represent the radius, which is 3, right? You would notice it here. If you look at it carefully, that should be 3, right? 1, 2, 3, right? To the center, right? That is 3. And going up from here to here should be 3. Here to here should be 3 as well. Just make sure it looking a little legit. Yes, it's a sketch, but make sure it looking a little legit, right? And that is basically the answer there for that. Nothing else to do there. Yeah. And that is 3 quick marks, right? So that is part B, I and I. Now we're looking at the final question. This is it. This is the big one. Yeah. Calculate the modulus and principal argument of z is equal to u on v to the power 5. Yeah, so they asking us to find this. The first thing that would come to my mind is like, what u is. Let me write down what u and v is. Let me do that first. Try to see. Yeah, that is u and v, right? From the previous question, right? That's what they told us u and v was. So you might think, well, let's put u and v and then multiply by the conjugate of the denominator and try to find out what is the real part and the imaginary part, and then find the modulus and the principal argument. That is all well and good, you could do that. But you might get frustrated doing that because there's a lot of work going on behind the scenes. Or we could use this little kind of rule that we know, or that we should know, that makes it easier. And as I told you all, as I said previously, time is of the essence in this exam, right? So what we need to do here next is let's look at finding the modulus, right? And this is the rule that we want to employ, right? With complex numbers, we could do this. We want to find the modulus of, what is it? It's actually, for this one here, is actually the modulus of u on v all to the power of 5, right? But you could bring that modulus outside to express it as the entire thing, right? And then we could express it as this here, where we have the modulus of u to the power of 5 on the modulus of v to the power of 5. So that's basically what we need to use. We're using this rule, and we have what is u, we have what is v. So it's just a matter of finding the modulus of u and v, and then we could raise it to the power of 5, right? That's basically it. You have this, and that would be the final answer there, right? What I just did basically was this. The modulus, that is a formula that we should know for the complex number. The modulus, or the length of the complex number, right, is the square root of the real part squared. The real part is 4, right? The imaginary part squared, right? And that's basically it. And then we just raise it to the power of 5, right? And all I did here in the end, you do the same thing for v in the denominator, and I just took everything here and plug it into my calculator. It's no sense looking at it and getting flustered. Plug everything into a calculator, and you should get this as the length, right? Then what we have to do is find the argument. That's the next thing, right? So let's find the argument, and this is where it gets kind of interesting. The argument also has a rule that we need to know and learn. This does come in real handy because it could come and make things, just make it so much quicker, because I said time is of the essence in the exam, right? So if you could recall these rules, right, for the argument and the modulus of the complex number, it makes life really easy. So this is the rule here, and this rule, every time I see it, it reminds me of the rules when we looked at logs. For those who here looking at, or who did add maths, it really reminds me of log rules, where we could bring down the power here, right? You could bring down the power, and then the log of, if you have two terms dividing by each other, is the log of the numerator minus the log of the denominator. And then all we do is find the argument of u and argument of v, which we have here, u and v. And how do we find the argument? The argument of a complex number is the tan inverse of the imaginary over the real part, right? So that is the next thing to do. Let's look at just finding the argument of these two, and then we will dance and try to find out the big thing, right? So let's deal with it in pieces and then bring everything together. That's what we're doing here now, right? So I'm just doing it in the corner here at the bottom, and this is what we're noticing here, right? And next thing too with the argument, just to bring this up, remember with the argument, you want to make sure you know the region to which the complex number in question it lies, right? So in this question here, when we're looking at the argument of u, right, I just come in the corner here, you would see that it's 2 over 4, right? Remember, this is a imaginary over a real, tan inverse of a imaginary over a real. So if you sketch it, I always say do a sketch, tan inverse, and this is a rule that you need to know, right? If you find tan inverse and the complex number lies in the first quadrant, that is the answer in the calculator. Make sure your calculator also too is in radians, not in degrees, right?
Yeah, I don't know quadrants here.
Yeah,
some tricks.
Yeah. Well, nothing major, but yeah, right? So you just have to make sure the rule is that the angle must lie from negative pi is less than theta, which is less than pi, right? So that's basically the rule there. Yeah, so it's negative pi is less than theta, which is less than or equal to pi, right? So that is the region in which it must lie. And this will satisfy that. Also too, this will satisfy that, because this as well will lie in this quadrant, this first quadrant. So everything good there, right? That's a thing that you need to pay attention to, which quadrant it lies in. Because if it lies in the first quadrant, the answer is as what the calculator gives. If it lies in the fourth quadrant, also the answer is as what the calculator gives. The second and the third quadrant do it. That is where you have to know when to add pi and when to minus pi. So that's the key things there. Also, so let's move along, right? We found what is the arg of u and the arg of v. Cool. That is this here and this here. Let me put everything together now, right? We almost done. So let's do this here and see what we get. So there's the answer here, right? But remember I told you all, negative pi, this angle, the argument, right? This is the region it must lie. Negative pi is less than theta, which is less than or equal to pi. But pi is actually what? Pi is 3.14. Yeah, pi is 3.14. This outside of the region. So that can be an answer, right? So what we need to do here is actually add 2 pi. In some cases, some people might add 1 pi. But if you add 1 pi, that wouldn't give you the correct answer, right? You need to add 2 pi and your final answer would be this here, right? Also for this particular complex number, it actually lies here. And the angle here starts off from here and it comes around up to here, right? But the angle that we need to find is always the angle that it makes with the positive x-axis, right? And it makes a 360. And as a result of it making a 360, which is 2 pi, that's why you need to add pi so that we could find this angle here, like this angle here. That is the angle I need to find. Because also another rule with regards to complex numbers and the argument of the complex number, right, is the angle that it makes with the positive real axis. And that there would be the modulus and the principal argument of z, which is this, right? So that would be, yeah, that's basically answers there. You should just indicate correct to 2 decimal places. And well, you have also 2 irradians, right? 2.44, right? You just plug in these stuff into your calculator. That's really it, right? And I think that was it. That was the end of the question there. Yeah, so yeah, that's it.
I want to check something on my calculator.
What's that?
This can actually be solved on the calculator that I recommend. So let's say you want to find u over v. Change your calculator into
complex mode, yeah.
Complex mode.
Yeah, for sure.
And you're on radian, so you double check this.
Yeah.
And you can use the absolute here. Is there one for that? You can get the conjugate, you can get the argument. But if you want, you can use this. This ABS is really the modulus or absolute value. So you'd use that. And it gives you it, you put on fractions, and you actually just type in the complex number as is. This will really help secure the bag.
Yeah, for sure.
Shift and I and 1. So you literally type in out the question on your calculator to get the numerical answer. Shift and I know you all will be very interested in seeing this, so that's why I'm saying it.
Yeah, these real vibes.
And you get your 7.36. So you sure?
Yeah.
You sure that this is the correct answer?
Yeah.
With this too, the argument have a little problem with going to the power of 5, but you can use this rule and get 5 by the argument of u and v. Same thing, same setup. 5 shift complex. You can come back and watch the video to see the actual numbers that I'm pressing to get it, and you just type in your u and your v one time. 4 plus 2 shift I and 1 plus 2 root 2.
Yeah,
so I have a shift. Yeah, that should be good. So you have your answer to go.
Yeah.
Alright. Okay. So thanks for the pure maths. But if you really want to get into it and get a full lessons package, get all the classes we did in pure maths, the entire topic, watch over everything. You like the teaching, you like the vibe. You can just WhatsApp this number, and you can join any one of our pure maths class, pure maths unit 2, pure maths unit 1 classes, or any subject offered at the TSH by WhatsApping this number. It's $200 per month. Love and blessings till we meet again. 2 videos for today. Who knows? We might do another one. We might do another one.